we've already introduced the derivative from the beginning of the course, which was to, a formula that tells you what the slope is. But then there's a second derivative. So we'll just refer back to our good old friend x squared. It's a good place to start. So if f of x was x squared, f prime of x is 2x. We already know that. So 2x gives the slopes of x squared. The second derivative is the derivative of the derivative. So we just keep going. We take the derivative one more time. The second derivative should give you the slopes of the first derivative. The mechanics of finding the second derivative aren't that much different, right? Like derivative of 2x is just 2. If you consider 2x in the context of a y equals mx plus b, then yeah, like m is 2. M is the slope of like the linear function, which is 2x. If you consider, my parabola, but then I have like the derivative being this, and you can clearly see that the slope is 2. But when I draw that out, that's like a flat line. You can keep going, actually. You can take as many derivatives as you want, right? Like I can do a third derivative. Derivative of 2 is just 0. And then any derivative from then on, you can just add as many ticks as you want. You start using Roman numerals. So you can do f Roman numeral 4, but that's still 0, etc. We only have been taking the derivative once so far, but once you know how to take derivatives using all the techniques we've already been doing in class, you can literally just keep going, right? We can circle back to sine. I'll do it Leibniz style for the Leibniz fans in the audience. So dy over dx is cosine x, right? But then if I wanted to write out the second derivative in Leibniz style, you would do d squared y over dx squared. The second derivative would now be minus sine x. I'm not squaring anything. Leibniz notation is strange. It's not really a fraction, and it's not really a squared either. But if I wanted to take the third derivative of minus sine would be minus cos. And then, fourth derivative, d4y dy 4. Derivative of cosine is minus sine. Minus times minus takes us back to sine. For certain functions, you have some fun patterns. Whereas, for polynomials, the degrees just keep going down until there's, nothing left really to take derivatives of. For trigonometric functions, it's a little interesting. You might have some fun patterns there, some fun loop the loops. So that's interesting. Let's do an example. Find the second derivative, x equals 1, I should say. All right, so let's take the first derivative, which is, we can move a little faster now. That's just quotient rule. So it's 1 plus x minus x. 1 plus x. I know the derivative of the numerator and the denominator is just 1, so I'm not going to write the 1 in. And that we're done. In order to take the second derivative, I don't even need to use quotient rule anymore. You could, but numerator prime is 0 because of the constant rule. So I'm going to convert that into an exponent. Is the bottom not squared? Yes, it is. That shouldn't make that much of a difference for my second derivative strategy, which was to just use power rule. So -2, 1 minus x, -3. But wait, Mr. Eusebio, don't forget your chain rule again this time. Did I copy that down wrong? Yes, I did. It's supposed to be plus. It clearly says plus there. Oh my gosh, see what happens when we just rush into things. -2 over 1 plus x cubed. Okay, so f double prime of 1 is -2 over 1 plus 1 cubed. -2 over 2 cubed, which is 8, -1/4. Ta-da. So we've been talking about first and second derivatives and higher order derivatives so far in the abstract, right? You can keep taking the derivative of a derivative and you can keep going that way. But I also told you that we are going to introduce applications. The first application that we see for higher order derivatives would be for physics. So if we consider like motion, so let's say Jarvis to Algonquin would be 2 hours, 52 minutes, 278 kilometers. We're assuming a lot of things, right? Like Google is assuming like, the current rate of traffic, and it's assuming that we follow these roads exactly. So there's a lot we can figure out from here. I mean, we can figure out the speed, right? Like velocity, sorry, I should say velocity is distance over time. So I have to do 278 kilometers divided by 2.87 hours. 96 Ooh, that's fast. I'm going to go 97 kilometers per hour. Assuming we drive 97 kilometers per hour, we can get to Algonquin Park from Jarvis 2 hours 52 in 2 hours 52 minutes. But that, again, I'm not starting out driving down Wellesley at 97 kilometers per hour because, that would be incredibly dangerous. It's assuming an average speed from Jarvis all the way to Algonquin. If you average out your speed, it would be 97 kilometers per hour. So that's assuming like a average rate of change. In the moment, like when I'm turning out, that's probably like, I'm going 10 kilometers per hour. But if I pick a point where I'm on Wellesley, that would maybe be, you know how slow downtown gets. Once you're on the DVP, you would be gunning it once you're on the DVP, right? If you've ever done highway driving with your instructor, the instructor is always telling you, speed up. You got to match the speed of the highway, right? Like, so you're driving local, which is like, you try and keep your speed limits. And then you got to get used to actually speeding up over here on the ramp. And you got to speed up to match the speed of the highway. What's that word? What's that word called when we're speeding up? Accelerating. Yeah, exactly. So S double prime, the second derivative would be acceleration. So if the original function is just a measure of your distance, I took the derivative of that, I get velocity. I took the derivative of that, I get acceleration. At the end of the day, we're looking for slopes and we're looking at rates of change. So that will come by in this graph here. And I'm just going to copy and paste the graph from, or not. We can literally graph that. That's not even that hard. Just to make it like I'm not cheating and like we're all copying along, I will just recreate the graph for you. The Y values, it doesn't look like they matter, but it peaks at 2, bottoms out at 6. It kind of crosses like a thing here at 4. It's a very subtle shift. Okay, there you go. So an object is moving along a straight line and its position to the right of a fixed point is given by the graph shown. When is it moving right? When is it moving left? And when is it at rest? So the object is moving across a straight line. What object? What are you talking about? I'm assuming they probably mean like particles and stuff, like, like you're probably doing research on the Large Hadron Collider or something like that. When the graph is going up like this, that can only mean I'm moving further away from the fixed point. So if you look at the diagram, I will redraw the diagram here. The fixed point needs to be like to the left of the object because the object is to the right of the fixed point, right? So I'm keeping track of where it is in relation to a fixed point on the right. So the object could be anywhere here. So it could be here, could be there. So if you take a random object here, you're sort of like moving left and right alongside the line. When the graph is increasing like this, my object is moving away from the fixed point. So it's moving right on the interval between 0 and 2, moving left anywhere from the section where t is 2 up until t is 6. It's moving towards the object, right? So the first half of my graph, it's moving away from the object. The second half, it's moving towards the object. So it's moving towards the fixed point. So it's moving to the left. So from t equals 2 to t equals 6, the object is moving to the left. But then at t equals 6, the object is moving away from the fixed point again. And t greater than 6. We're going to assume it keeps going that way. So at rest is exactly where I'd like to be. At rest is, you're not moving left, you're not moving right. That happens at these points, right? Like there's a split, there's a brief moment where the object is moving and the object in question has decided to move back towards. So when you're moving away from the object and then suddenly you decide to move back, there's a moment where you're not moving because you have to sort of change directions. So the moment right before you change directions, you're at rest. So at rest at t equals 2, t equals 6. Okay, so that's how we read it graphically. Let's do one algebraically. All right, so this one's a long one, and this one is an example where we're gonna put a lot of these ideas together. So example 3. All right, so the position is given by equals 6t squared. T is in meters, t is in seconds, t is greater than or equal to 0. So obviously you can't have negative time, so we're only concerned for this function when t is greater than 0. Now we have a bunch of questions to ask. Quite possibly, you're checking particles. Might be a particle physics thing. It might be a gas thing. Tracking the positions of molecules is my guess. But we're really just doing the math, right? So we're trying to figure out following questions based on what we know. The original function tells you what the position of the object is. That would mean the rate of change of position is velocity. So v of t is derivative of the position, 12t minus 3t squared. Acceleration would be p double prime, which is v prime. These are all different names for pretty much the same thing. Okay, so velocity at 2, bp prime of 2. Let's just plug in 12. So 24 minus 3 times 4. So it's 24 minus 12, which is 12. Don't forget your units. If p is in meters, t is in seconds, that is 12 meters per second. So to find acceleration, we do something similar. We plug in 12 minus 6 times 2. So it's 0 meters per second squared. The object is moving, but it's moving at a steady speed of 12 meters per second, right? It's not speeding up. It's not slowing down. It's moving at a consistent 12 meters per second. So my object's at rest when velocity is 0. V of t is 0. So again, when acceleration is 0, it doesn't mean you've slowed down or stopped. When acceleration is 0, it means you're moving at the same speed you are. You're not speeding up. You're not slowing down. In order to check for when we're at rest, we need to check for when velocity is 0. So we set 12t minus 3t squared to equal 0. There's two answers. One answer is when t equals 0. The other answer is when t equals 4. So therefore, object is at rest at t equals 0. The other route we get from t equals 4. Okay, which direction is it moving in at t equals 5? To check direction, speed by itself doesn't tell you if you're going backwards or forwards or if you're going east or west. Let's just plug in v of 5, which is p prime of 5. 12 times 5 minus 3 times 25, which is 60 minus 75 minus 15. So velocity at t equals 5 is minus 15. Again, that's meters per second. So it's moving in a negative direction. So D is asking when the object is moving in a positive direction. So we need to check when velocity of t is greater than 0. So we need to check for when 12t minus 3t squared is greater than 0. We have to set up an interval table. We already have the intervals that we need. They're basically, you take your number 9, you take your points from 3b, which were 0 and 4, because they are at rest here. The implication is between 0 and 4, I'm traveling in one direction. There's only one way I could go. I could be going left, I could be going right. But if I'm going right to left, there's a point where I switched, right? When I'm changing directions, I'm at rest. 0 to 4 is one interval. Anything past 4 is another direction. So again, if the object somehow changed directions between 0 and 4, that implies that there's a point where it's at rest in here, but that's not what the function is saying. So let's do our interval table. From part C, we already knew that it's moving negative because I plugged in a 5 and we saw that it's negative. For this interval, let's plug in something like 2 and see what happens. So if I go 12 times 2 minus 3 times 4, so it's 24 minus 12, it is 12, which is positive. By analyzing it according to the interval tables, velocity is positive when time is in between 0 and 4. Last part for this question, when does the object return to original position? So original position is when time is 0. So let's plug in t to the original thing. So p of 0 is 6, 0 squared minus 0 cubed. So that's still 0. So the other times, all right, so now we're like, do we use the original function? Do we use the velocity? Do we use the acceleration? We stick to the original function because we're just looking for time. So when is it at its original position? So we set the original function equal to 0. So we go 6t squared minus t cubed equals 0. Factor out a t squared. 6 minus t. So the other time is from here, which is t equals 6. So therefore, the object returns to original position at t equals 6. All right, last question. The path of a baseball is given by the function s of t, 5t squared plus 30t plus 1. So again, time goes in, position comes out. What is the max height of the baseball? And then B, how fast is it going 1 meter above the ground when caught? It's a parabola question. You might remember these from grade 10. Having to complete the square, finding the vertex. You don't need to do that anymore. Let me show you how we can solve this using calculus. When you're throwing a ball in the air, at some point, it's going to peak. But when it peaks, it's actually at rest. It's not that it stays there for too long, but because it's going from up to down, at its highest point, it's actually at rest. And when it's at rest, you're implying the velocity is 0, right? Because it's switching from a positive velocity to a negative velocity. So all you really need to do there is we go s prime of t is negative 10 t plus 30. And then we solve for 0. Negative 10 t plus 30 equals 0. Fast forwarding a bit, we move the 30 to the other side, divide by 10. T is 3. So max height occurs when time is equal to 3. We plug the 3 back into the original function to get the real height. So s of 3 equals negative 5, 3 squared, plus 30 times 30, which is 90. So 3 squared is 9. 9 times negative 5 is 45. Minus 45 plus 90 plus 1, 46. Consider how you solve the question like this in grade 10 versus how we're solving it now. That went by a lot faster, right? I took the derivative, set equal to 0, plugged it back into the original, and that's it. I've essentially found the vertex, right? The vertex would be 3 and 46. If you are so much better at calculus now than completing the square, you can easily just do it that way. B, how fast is it going 1 meter above the ground when it is caught? So I'm trying to find the slope at 1 meter above the ground. So we have to set s of t equal to 1 because that's when it's 1 meter above the ground. Minus 5t squared plus 30t plus 1 equals 1. Subtract out the ones. I get minus 5t squared plus 30t equals 0. Factor out the minus 5 5t t plus 6 equals 0. So t can be 6. Sorry, that should be a negative on the inside because I factored out a negative number. So t equals 0. So the 2 times the ball is 1 meter above the ground are at t equals 0 and t equals 6. At t equals 0, the ball was just tossed, right? So I'm more concerned for when it's caught. So we're going to plug 6 into my s prime. So that is minus 10, 6 plus 30. So negative 60 plus 30 equals minus 30 meters per second. Okay. Oof.